All right, so now we're into the last lecture, and we'll move into mixed ANOVAs. So up to this point, we've considered between subjects designs and repeated measures, or within subjects designs, independently. So remember, our between subjects designs where we had each person was assigned to only one condition. They're exposed to only one level of the independent variable. And a repeated measures design was where each person was exposed to multiple levels of the independent variable. A mixed design is just a combination of both types of designs. You have one, or at least one between subjects factor and at least one within subjects factor. So returning to our goal setting example, we might look at the effects of goal setting, but over time. And so in this case, we have randomly assigned people to either a control, a do your best, or a difficult specific goal condition, and measured their performance at 2 points in time. So goal would be a between subjects factor because each person's only assigned to one level of the goal manipulation, and time would be a within subjects factor because we've measured them at 2 points in time. So I think it's easiest to dive right into an example, and for this one, we'll return to our PTSD example from the other lecture. So recall that our dependent variable was the number of reported PTSD symptoms that a patient experienced. But this time we're looking at not just are the symptoms changing over time, but are the symptoms changing over time as a function of the type of therapy that the person receives. So specifically, we had 27 participants who were measured at 3 points in time, once before they received therapy, once immediately after, and once 3 months later as a follow-up. But they were randomly assigned to 3 different types of therapy. So 9 subjects received a stress inoculation therapy, 9 received a prolonged exposure therapy, and 9 received just general counseling. So our data are shown in this table and plotted to the figure to the right. In the figure, we can see that we have 3 groups represented by each line: the stress inoculation therapy, SIT, the prolonged exposure, and the counseling, represented by each of these 3 lines. And we're measuring each participant at 3 points in time: the pre-period, the post-period, and the follow period. Looking at our data, we can see that participants are assigned to either the stress inoculation, the prolonged exposure, or the counseling, and that each participant provides 1, 2, 3 observations. So there is a between subjects factor, where participants are in only one condition, and there's also a within subject factor. Thus, the appropriate analysis plan is the mixed ANOVA. As always, we need to partition our variance, right? We have a total amount of variability in PTSD symptoms. So there's variance. Not everyone has the same number of symptoms. What we're trying to do is partition that variance into its various components here. So the first is between and within. Between is, do people on average vary in the number of symptoms? And that variance can be broken now into 2 different parts. One is how much of that variance is due to the type of therapy that they received, which group that they were in, which condition that they were in. And whatever's left over is error. So anything that's not explained by the group, but is still between subjects variance, is just error. Likewise, we have within subjects variability. Here we have an effect of the treatment, or in this case, it's just time, the passage of time. How much is due to the passage of time? But you also have an interaction term. How much is due to the effect of time, but also the type of group that you're in, so the time by group interaction. And then likewise, what's left over is error. So when we go to assemble our source table, it's getting a little bit more complicated now. We have lots of parts, but these parts correspond to that partitioning of variance. We're partitioning the total variance into first between and within subjects, and then from there we partition the between subjects into group and error, and the within subjects into time by group interaction and error. As always, start with the degrees of freedom. They get pretty complicated here. We have lots of things going on, and to be honest with you, this isn't something that I have memorized. This is something that you should look up and make sure that you get it right, because there's lots of parts here. So the group, we'll use G to represent the number of groups now. Before we used K, but now we need K for something else. So we'll use G to represent the number of groups. And so our group degrees of freedom is, as usual, G minus 1. The error term is our number of groups times the number of people per group minus 1. So lowercase n is the number of people in each group. Our repeated measures factor, I've called it time here, but remember, it's not always time. It's whatever is repeated, whatever factor is repeated, is our number of repeated measurements, K minus 1. Whoops. The time by group interaction is just the number of people, it's just the product of those two degrees of freedom. So G minus 1, which is our group degrees of freedom, and K minus 1, which is our repeated measures degrees of freedom, and it's just the product of those. The error term is that product times the number of groups, and as always, our total degrees of freedom is our total number of observations, represented by an uppercase N, minus 1. So we can go ahead and fill those in. We had 3 groups, so that's 2. We had 3 periods of time, that's 2. The interaction is 4, and so on and so forth. Computing our sums of squares total is the same as always. We have to find our grand mean, which is our mean ignoring all the factors. It doesn't matter what condition you're in or what period of time it is. It's just the mean of all the data. In this case, it's 17.68. And recall that we can subtract each score from, subtract that mean from each score, square the result, take the sum. In this case, it's 6,003.65. So I can go ahead and fill that into my source table. Next, we can compute the between subjects sums of squares, which is the same as we did for the repeated measures ANOVA. We have to find each participant's subject mean. So participant 1, their mean was 15.33. I take the average of these 3 values. Participant 2, their mean was 22.33. Again, it's the mean of their 3 observations, and so forth. I can do that for everyone. Compute these subject means, x bar s. Subtract the grand mean from that value. Square the result. And now I have to remember to multiply by the number of observations, or the number of observations that computes this subject mean. So that's K. Each person has 3 K, 1, 2, 3 observations. And so we have to multiply their deviation by that number of observations. So we get 15.33 minus 17.68 squared times 3. Do that for each person, take the sum, and we get 2,152.32, which we can pop into our source table. Now, our within subjects sums of squares is what's left over. Remember, we have total sums of squares. We've said, well, this is how much sums of squares is between subjects, so whatever is left over must be within subjects. So to find the within subjects, we can just subtract the between subjects from the total. So now we can start thinking about our sums of squared group. So basically doing the between subjects part of the analysis. To do this, we need our x bar sub g, our mean for each group. So our mean for our stress inoculation therapy is just the mean of all the observations within the stress inoculation therapy condition. In this case, it's 16.89. And do the same thing for prolonged exposure and the same thing for counseling. Next, I take that group mean and I subtract the grand mean and square the result. And then I have to multiply it by the number of observations that form that group mean. In this case, it's n, the number of people per group, times k, the number of repeated measurements, because there's 9 times 3 observations in this yellow square that made this yellow mean for the stress inoculation therapy. So I take 9 times 3 times the deviation between the grand mean and the group mean squared, and do that for each group. Finally taking the sum, and I find it to be 37.80, which I can pop into my table. Now for the error term, I have at the between subjects level, this is sort of like my total for the between subjects level. And so there's only 2 parts, so I know whatever is left over is error. So another way to say that is to compute your sum of squares error at the between person level, it's your sums of square between subjects minus the sums of squared group. It's what's left over at that between subjects level. Next, we can compute the sums of square for the repeated measures factor. So sums of squares time in this case, where we need the mean at each observation period. So the pre, post, and follow-up means. So x bar k, the mean at each repeated factor. So in this case, that's 25.33, 14.44, and 13.26. And remember, we have to, well, compute that deviation and square it, but then we have to weight it by the number of observations. So in this case, it's n, 1, 2, 3, 4, 5, 6, 7, 8, 9, n people per group, times 3 groups, 1, 2, 3, n times g. So we have 9 times 3 times the deviation. I can do that for each of my observation periods. Take the sum, and that is my sums of squared for time. In this case, 2,391.80. Next, I can compute my sums of squares cells. Remember, when computing interactions, the first step is the sums of squares cells, which is not the interaction term. It's a step along the way, but it's the first step that we have to do. So here I've computed the mean for each cell. So there I have my stress inoculation therapy pre-cell, my stress inoculation therapy post-cell mean, and so on and so forth. Next, I compute the deviation of each of these means from the grand mean. So each time I'm subtracting out 17.68, squaring the result, and multiplying, this time just by n, the number of people in that cell. So that is 9, because there were 9 people per condition. So I find my sums of squares cells to be 2,721.65, but recall that I have to remove the sums of squares from my main effects. Here I have a main effect of group and a main effect of time. So my sums of squares interaction term is sums of squares cells minus sums of squares group minus sums of squares time, which comes out to 292.05. Finally, my error term at the within subjects level is what's left over at the within subjects level. So I had a within subjects sums of squares, 3,851.33, and I subtract out time and the time by group, the other parts that are at the within subjects level, to leave me with my error term. The next part is the same that we've always done. Mean sums of squares is just our sums of squares divided by the degrees of freedom. So we just divide across these columns. And our F here for the between subjects, we divide our group mean squared by our between subjects error. So 18.9 divided by 88.11. Likewise, at the within subjects level, we're going to divide by our within subjects error term. So 1,195.9 divided by 24.32. 73.01 divided by 24.32. And so now we have to go to our F table, but let's look at our degrees of freedom. At the between subjects, we have 2 and 24 degrees of freedom for our group term. For our time, we have 2 and 48 degrees of freedom. And for our interaction, we have 4 and 48 degrees of freedom. So we're going to have 3 different F criticals here. So first, for our group, we had 2 and 24 degrees of freedom. So our F critical is 3.40. We come back and see our F is far less than that. So I put a little NS here to say that's non-significant. There's no significant effect there. For our time factor, we had 2 and 48 degrees of freedom. So no 48 in the table. I just went down to the next nearest, which is 40, and found that our F critical was 3.23. And since 49 is well above that, we do have a significant effect. Next, for our interaction term, I had 4 and 48 degrees of freedom. Again, no 48 in the table, so I just went to 40 and 4. And I had 2.61 as my critical, and our observed is greater than that, so that is also significant, which I've indicated with an asterisk here. So you might write it up something like this. As evident in figure 1, there's a main effect of time. So report your F and your degrees of freedom. Report your mean squared error and your p-value. And there's also a therapy by time interaction. Again, your F, your mean squared error, and your p. There's no main effective condition, okay? But really, to further understand these analyses, we have to do some follow-up tests, right? We have to probe this interaction, just like we did with between subjects interactions. We have to know, is this decrease significant? Is this, which of these means are different from each other? There's lots of different questions we could ask here. Just knowing that there is an interaction doesn't really tell us very much. It doesn't tell us about the form of the interaction or how these effects differ. So we have to go on and probe our simple effects. The within subject simple effects for the mixed ANOVA are pretty easy because we can just use the error term from the omnibus table. We can use our mean squared error from the within subjects part of our omnibus source table as our estimate of population variance. And then we can just move on as normal. So for example, to compute the simple effect of time at SIT, stress inoculation therapy, we are looking at the effect of time. Does time have an effect on PTSD symptoms only within this stress inoculation therapy condition? We're not paying attention to the rest, so I've blurred it out here. So just like we did simple effects before, we need the means of each time at that condition, and we need that marginal mean for the overall mean for just the stress inoculation condition. Right? So I have the mean of pre at SIT, post at SIT, follow-up at SIT, and I'm going to compare that to the overall mean of the stress inoculation therapy. So in this case, I compute my deviation between my pre and my marginal mean, my post, which is 10, and my marginal mean, 16.89, my follow-up, 13.78, and my marginal mean, 16.89, square each result, and multiply by, in this case, 9, because I have 9 people in that condition. Right? 9 people made up this pre at SIT mean. 9 people made up this post at SIT mean. So we're going to multiply by the number of observations there. I can do that for time at SIT and find the sum is 1,414.22. And remember, I can go ahead and pop that into a simple effects table. So here I have time at SIT, time at pre, and time at counseling. I'm looking at the simple effect of time. Does time have an effect at each condition? For my error term, I've simply just pulled this right from my omnibus table. I didn't have to do anything. I I already did the work here. So I think it helps to look at the figure. We are looking at within one line. So I just did for the SIT condition, right? Is this solid line, is there an effect? We're just looking at the effect of time on the DV at one level of the other independent variable of the group. And we find, so we have an F of 29.07 with 2 and 48 degrees of freedom. I'll look it up later, but we can say pretty certainly that that's a significant effect, right? That's a large F. It's going to be larger than what is the critical value. So we do have a simple effect. So there does seem to be some change. Recall at this point, we had 3 observation periods, pre, post, and follow-up. So we don't know which of those 2 are different. That would require further, probably t-tests. But we know that there is an effect of time at the stress inoculation. Or another way to think about that is for people within that condition, time did have an effect. We can go and do the same thing for the prolonged exposure condition and fill that into our table. And we can do the same thing for the counseling condition and fill that into our table. We had 2 and 48 degrees of freedom. So for our F, we have 2 and 40. I go to the closest without going over in my table. So my F critical is 3.23. So all of those effects are significant. So within each condition, PTSD symptoms did change over time. Recall, we could then do additional follow-up tests. I'm going to go back to the figure. Within each of these lines, there is a change over time. But let's just look at the solid line here, this solid circle line. Is the pre different than the post? Probably. That looks like the biggest change, but we haven't tested that yet. We don't know. More importantly, is post different from follow-up? Is this little uptick here, did people experience more symptoms, or is this non-significant? We don't know. We know that at least 2 of these means are different. That's what that first level of our simple effect tells us, right? We did the F, but then we would need to follow this up even further using t-tests like we showed in the previous lecture. So that was simple effects at the within subjects level. At the between subjects level, we have a little bit extra work to do. It'll be worth it. It's going to give us higher quality results than the alternative, which we'll also explore, but we have to do a little bit of extra work. Specifically, we can't just pull that mean squared error from the omnibus table. I'm going to go back a minute. With the within subjects test, that's what we did. When I wanted my error term for my within subjects test, I just pulled it directly from the omnibus table. But for my between subjects test, that's not the case. Instead, we need to compute a weighted mean squared error as a function of our sums of square from our error terms of both our between and within parts of the model. I've indicated with B and W, between and within, as well as our degrees of freedom from the between and within parts of the model. So our sums of squared error between is right here, 2,114.52. Our sums of square error within is 1,167.48. The degrees of freedom for our error between is 24, and our degrees of freedom for our error within is 48. So we can pop those into this equation and solve for our between subjects mean squared error that we'll use for our simple effects. This is our best estimate of population variance at the between subjects level. Likewise, for the degrees of freedom, we have a similar, we have to take this equation, and basically the sums of squares for the two parts of the model, which is A and B. And the A and B is just so you can keep them straight. So whichever is the within and whichever is the between, now in the denominator, you have to keep them together because you're dividing them. So in this case, my sums of square between is 2,114.52 and within is 1,167.48. So that's in my numerator, square the whole thing. Then I just have to be sure in the denominator to keep my between subjects sums of square over my between subjects degrees of freedom. And likewise for the within. We get 50.17. We can't have fractions here, so I just round down to the nearest whole number. Just be conservative and just go down. So here 50.17 becomes 50. I made a little Excel sheet that does this where I can just type in these numbers. So I only had to get it right once. Right? I made sure it was right. This can be, this can be a little bit confusing. It's not that hard, but there's room for error here, human error. So make an Excel sheet that you can type these numbers in and it'll pop out your mean squared error and your degrees of freedom, and then you'll always have it. And then you'll know it's correct and you can use it for the future. That's my recommendation, at least. So I go ahead and I create my between subject simple effects table. So now I'm looking at group at pre, right? Because it's between subject. Does the group, which is a between subjects factor, you're only in one group, did it have an effect at the pre time? Did it have an effect at the post time? Did it have an effect at the follow-up time? So I filled in my degrees of freedom and my mean squared error. I backfilled this in just by multiplying these values, but we don't actually need this sum to square, right? We're just going to use the degrees of freedom and the mean squared error. So if I'm looking at the effect of group at pre, now I'm only looking at pre. I'm not dealing with post and follow-up at this time. So I have a mean for each group: stress inoculation, prolonged exposure, and counseling at the pre-level. And I have my marginal mean for the pre, the mean going down the whole column. So the mean of these first 9 observations, the SITs, is 26.89. The mean of the next 9 observations is 25.22, and the mean of the last 9 observations is 23.89. The mean of the whole column is 25.33. So I can compute my squared deviations of each group mean from that marginal mean. So 26.89 minus 25.33 squared times lowercase n, the number of people in each group, the number of people that made this mean of 26.89. I add that to my next deviation, 25.22 from the grand mean, or marginal mean, excuse me, and 23.89 from the marginal mean. And I get my sums of squared group at pre is 40.67, and I can pop that into my table. I had 2 degrees of freedom because I had 3 groups: stress inoculation, prolonged exposure, and counseling. So I can divide across to get my mean sums of square. I can divide my mean sums of square by my mean squared error that we just computed, and I get 0.45. We know that that's non-significant because it's less than 1. I don't even have to look it up. Any f that's less than 1 is non-significant, so we know that's non-significant. This makes sense. Let's look at the figure. We just ran this simple effect. The effective group are these 3 dots, the dot, the square, and the diamond. Are they different from each other at pre? That's what we just ran. Looking at the figure, it looks like, no, they should not be. They're all pretty close to each other. I mean, maybe they're a little different. Maybe this will be statistically significant, but it's, these look like pretty small effects. And if we think about this, what was our design? It was symptoms before they got any therapy. So we would expect there to be no difference of condition, because at this point, condition didn't actually differ, because they hadn't received the therapy yet. They hadn't actually received the what made it the condition. So it makes sense that we would find no simple effect at this pre, both looking at the figure and if we just think about our data, think about what the experiment was. Doesn't mean that it had to be that way. That's why we have to test it, but it makes sense that it came out that way. Sorry, I'm lost in my slides. This would happen if we were in this is what would happen if we were in the classroom too. So it's the full experience. Okay. So now we can move on and do the sums of squared of group at post. Same thing that we just did. We did pre, now we're doing post. So I find my mean of each group, SIT, prolonged exposure, counseling, the mean of the entire column, and I can compute the sums of squares of group at post and fill that in. And I can do the same thing for follow-up. Follow-up, again, I can tell it's non-significant, which makes sense. I'm going to go back to the figure real quick. At follow-up, look, the lines are all right on top of each other, so we wouldn't expect that to be significant just looking at the plot, and indeed it's not. Perhaps a little surprisingly, though, our F critical was 3.18. We had 2 and 50 degrees of freedom, recall? 2 and 50 degrees of freedom. So our F critical was 3.18, and our simple effective group at post, which looking at the figure looked like it might be significant, was actually not. So there actually was no between subject simple effects here. There was no differences between groups. So we would be done at this point. We wouldn't go on to follow this up with t-tests at the between subjects level because there are no differences here. If we want to do this in SPSS, we would set up our data as I think you would hopefully expect, right? It's just a combination of the between subjects ANOVA and the within subjects ANOVA. So I have each participant, they're each in one of 3 conditions here, and they have 3 observations each. Make sure your variables are coded correctly. My subject number, I'm not doing anything with it, so it doesn't really matter, but it's still good form to tell that SPSS it's a nominal variable. It's a number, but it doesn't have any numerical meaning. More importantly, condition. I labeled 1, 2, 3, but those 1, 2, 3 don't mean anything numerical. 3 isn't higher than 2. It's just a name. So I have to tell it that it's a name. My other 3 variables are scale, which SPSS calls either interval or ratio variables. It doesn't distinguish between them. It just calls them scale variables. So to run this, we analyze general linear model again. Again, we're at repeated measures, same as we were last lecture. We have to define a repeated factor, same as last lecture. In this case, it's time, and it has 3 levels, so I can go ahead and add that. It asks me to define, okay, well, what's at time 1, what's time 2, what's time 3? So we have labeled those variables pre, post, and follow-up. I can go ahead and select those, click this arrow, and move them over. But I also now define a between subjects factor. I move my condition over to the between subjects factor. Same assumptions. We're doing a repeated measures ANOVA still, so it's the same assumptions. We have to worry about our test of sphericity, and here, no problem. Our Mauchly's test has a p that's greater than 0.05, therefore it's non-significant. Therefore, our assumption is met, and when we look at our within subjects test, we can look at the sphericity assumed line. Recall that for the quizzes, I will tell you whether it was assumed or not, or whether Mauchly's was significant or not. Looking at these values, we can see that SPSS produced the same results that we observed by hand, and so that is a good thing. SPSS splits the between and within subjects into different tables. So here we were looking at the within subjects table. Here would be a different part of our results, the between subjects table. And again, SPSS produced the same results that we calculated by hand at the between subjects level. If we wanted to look at our simple effects in SPSS, we could do something called splitting the file. So here I'm going to look at my within subjects simple effects by splitting the file. And what I mean by splitting the files, I'm going to come up to my data tab, come down to, it's literally called split file. And I'm going to say compare groups by condition. So basically what I'm saying is chop up my data into 3 different data sets according to each condition. That's what this does. So okay, I went and I set that. And now I come back to my repeated measures, ANOVA, right? Analyze, general linear model, repeated measures. And I'm not going to set up a between subjects factor because there is no between subjects factor anymore because I've split the data. Now I have 3 data sets, an SIT data set, a prolonged exposure data set, and a counseling data set. So within each of those data sets, there's no between subjects factor, so I could just get rid of that. And I'm going to run this within subjects ANOVA within each condition. And when I do that, I get this within subjects table, and it's actually 3 tables here, right? I have the SIT table, the prolonged exposure table, and the counseling table. You can see that because it says condition 1, condition 2, condition 3. And that's what those were labeled. SIT, prolonged exposure, and counseling. I can get rid of all my greenhouse geyser and these other estimates. I don't need them. And so I can just look at the sphericity assumed line. And when I look at my sums of square that I computed, the within subject sums of square, it's identical to what SPSS computes. And the mean square is identical for each time at SIT, time at prolonged exposure, time at counseling. So that's good. But SPSS computes this error term within each condition. Because remember, according to SPSS, what SPSS is thinking, can't really think, it's software, right? But what SPSS is thinking is that it has 3 data sets now. So when it runs the within subjects ANOVA on time at SIT, it doesn't know that these other conditions exist. So it's not using those other conditions to compute that estimate of population variance. Remember, our assumption of homogeneity of variance, which is super useful to us. If we assume that our data are drawn from populations that have equal variances, well then we can use all of that data in our simple effects to estimate population variance. Gives us a more stable estimate and more degrees of freedom. But SPSS, when you split the file, it doesn't know that you're doing that. Or it's not doing that. It doesn't know that those other data exist. It's only looking at the SIT condition. Then it's only looking at the prolonged exposure condition. It's only looking at the counseling condition, one at a time. So it computes a different error term for each one. And then you only have 16 degrees of freedom within each one. More degrees of freedom is better. So when we used our omnibus test, we had 48 degrees of freedom, and we always use the same error term. You can see the error term is bouncing around, 26, 36, 9. But we assume that that's just noise because we assume that that variance term should be the same. So this bouncing around is just noise. We don't like that. And that noise is costing us something, and we only get 16 degrees of freedom. So splitting the file is not a great strategy. It is useful. You can have SPSS do this part for you, do the heavy lifting. It computed the sums of squares, all that calculation we had to do. Well, SPSS will give you the exact same answer. So have it do the heavy lifting, computing these sums of squares for you. But then when you go to compute the F, compare it to the mean squared error from the omnibus table. Recall, that's for within subjects test. And so in this case, we can see that our F changes. It was 29 when we computed it, but it was 26 when SPSS computed. 14 when we computed it, 9 when SPSS computed. 11 versus 29. It didn't make any difference in this case. The levels of significance didn't change. It didn't change your interpretation, but it could, right? It definitely could. So splitting the file is convenient, but it has a pretty serious downside, that it estimates a different error term for each condition. You should use the omnibus error term. We can also split the file going the other way, right? That was our within subjects test, so looking at the effect of time, but then we want to look at the effect of, looking at the effect of time within each condition, within each type of therapy. But we can also look at the effect of each type of therapy, or the type of therapy at each time, between subjects, simple effects. To do this, we can go to our one-way ANOVA, because effectively we're just doing a one-way ANOVA at time 1, at time 2, at time 3. You know, a one-way ANOVA at pre, a one-way ANOVA at at post, and a one-way ANOVA at follow-up. So I can go one-way ANOVA, pre, post, follow, my factor. So basically I'm putting in each dependent variable. So I'm saying do an ANOVA on each dependent variable. It'll just do it 3 times. But I forgot to do something. Remember before I split the file? I didn't undo that. And SPSS still thinks it has 3 different data sets. You have to go and undo it. And so I got an error. And this will happen. Sometimes you get errors in SPSS. It just means you got to back up and go and try to figure out what you did. The errors are often kind of, they're not real useful, right? So reading this, it would be hard to know. So if you get this error, you can kind of troubleshoot this by learning from my mistake and know that it is, I didn't unsplit the file. Basically what it's saying is, you told me to run an ANOVA, which requires between subjects groups, but you don't have any between subjects groups because you have 3 data sets that have no between subjects groups. So go back to my analyze, and we'll go analyze all cases. So I'm going to undo that compare groups and go analyze all cases, and that'll fix it. So now I ran that one-way ANOVA, and I gave it 3 DVs, and so what it does is it just runs it 3 times. It runs it on each DV. So again, if I look at my sums of squares, group at pre, that comes out exactly the same. Group at post, that comes out exactly the same. Group at follow, that comes out exactly the same for my sums of squares. What's different is the error term. This is the error term in degrees of freedom we computed. Whereas SPSS does it on each DV. And so it's computing an error term each time. And thus you have way fewer degrees of freedom. So again, this splitting the file version is convenient, it's faster. And in this case, again, didn't lead to any different conclusions, but it could, and it will in many cases. So better off to do it by hand. And SPSS simply can't do what we did. It doesn't have that functionality. So you will have more accurate and more consistent results if you do this part by hand. All right, so before we go into the second example, I think I'll cut this video short and split this into 2 parts so it's not too long. So in part 2, we'll go through basically just another example.